Welcome back. Today's topic is magnetization and magnetic materials. We have already seen in unit number 1 with respect to dielectric materials, and we have also seen that the dielectric materials, they experience polarization when they are placed in electric fields. Similarly, all the materials, when they are placed in magnetic fields, they experience some sort of changes, and that is referred to as magnetization. So in the last class we have seen magnetic dipoles, and we have already discussed that every atom basically it behaves as a magnetic dipole, and these magnetic dipoles will be oriented in such a fashion that the net magnetic moment will be zero. On the application of external magnetic field, there will be a change in the net magnetic moment, and based upon the amount of net magnetic moment, materials will be classified. So I hope that by the end of this lecture, you will be able to classify the magnetic materials based upon the magnetization. And before going any further, let's have a quick discussion about how magnetization is measured. With the application of an external magnetic field, the magnetic moments in a material, they tend to align and thus increase the magnitude of the field strength, which means earlier there will be magnetic dipoles which will be arranged randomly, with net magnetic moment being zero or to some value. So with the application of external field, there may be a change in the net magnetic moment, and the increase or a change is given by the parameter called as magnetization, referred by capital M. Do remember, small m is the dipole moment, capital M represents net change in dipole moment, which we call it as magnetization, and it is defined as magnetic moment per unit volume. Okay. So, and its units are ampere per meter. Now, if I do take the relation between B and H, if there is no material, I can directly take it as B is equal to mu naught H. Now, because of presence of another material, and that material is experiencing magnetization, so I'll take it as the net field is given by B is equal to mu naught into H plus M. Now, the intensity of the magnetization, capital M, it is dependent on the magnetic moment, which is magnetic moment per unit volume of the substance when subjected to uniform magnetic field. The intensity of magnetization is proportional to the applied magnetic field, isn't it? And this relation, if you apply a stronger magnetic field, then we see there is a huge change in the magnetic moment. So it all depends upon how much magnetic field you are applying. So, and this relation between these two, magnetization and the applied magnetic field, is given by the symbol psi, which we call it as susceptibility. We call it as susceptibility. And this susceptibility, it is defined in your magnetic terms as M by H, the ratio of magnetization in the material to the applied magnetic fields. So in other terms, it is referred to as a measure of capacity of the material to get magnetized. Now, we will try to substitute the same one. See, this is our earlier expression, B is equal to mu naught into H plus M. So we know that M can be replaced with psi M, right? Sorry, psi H. So if I take this one common, I'll take it as 1 plus psi. Now this term is referred to as relative permeability, mu r. Okay, so if I consider this one as relative permeability, the relation between relative permeability of a material to the susceptibility is given by mu r is equal to 1 plus psi. So now B is equal to what I'll get, mu naught mu r H. And this complete term permeability is called as absolute permeability, the ratio of permeability to free space to relative permeability. Now, We'll go back to the types of magnetism. I hope now you have understood that magnetization is measured in terms of M. Some materials they'll get high value of M, some materials do have low value of M, or in terms what we can susceptibility. Some materials they do have high value of psi, some materials they will have negative, some materials will have very low value. So now we will see the different types of magnetism which we see in materials. There are three types normally considered as dia, para and ferro. In the recent past there are additional things also, what we call it as an antiferro and ferrimagnetism. So primarily we will discuss about these three, and next if we do have time then we will discuss about these two also. The first one, diamagnetism. It is a very weak form of magnetism which arises only when an external field is applied. So see, normally, which means that there is no, see this is the material, if you can see this is the material, if H is equal to 0 there is no magnetic moment, and if you are applying H here in this direction, the net magnetic moment is in this fashion. So in this, it is a weak form of magnetism which arises only when an external field is applied, and it arises due to change in orbital motion of electrons on application of magnetic fields. So in the absence of magnetic fields, there are no magnetic dipoles, and when a field is applied, the dipole moments are arranged in opposite to the field direction. So that's why for these materials which have this property exhibited, we call them as diamagnetic materials. And for these materials, if you see, the dipole moment is opposite to that of applied field, so we will take it as psi is negative. Since psi is negative, you know that mu r is equal to 1 plus psi, right? So it will become less than 1. Mu r becomes less than 1. And best example of these materials are copper, gold, silicon, zinc and aluminum oxide also. On the other hand, there are some materials which do have random magnetic moments which are cancelled out. So, and when you apply this magnetic field, they will be aligned in particular fashion. So when there is no application of external magnetic field, there is no net magnetic moment. If you apply it, then automatically they will be realigned. In this case, we will consider that the permeability is greater than 1, but not greater than 0. It is positive, and mu r is also greater than 1, but not very large. Okay, it is slightly greater than that of vacuum, and this type of thing is called as paramagnetism. On the other hand, if this ferromagnetism, in ferromagnetism, there are some materials which possess permanent magnetic moments. In earlier case, the magnetic moment was 0. But normally in some materials, we do see even without the presence of magnetic field, we will be having some magnetic moments. And that property is called as ferromagnetism. So, if even in the absence of magnetic field, you are having magnetic moments, see, these arise due to uncancelled electron spins by virtue of their electron structure. So, ferromagnetic materials have incompletely filled d orbitals and hence unpaired electron spins. Their susceptibility value is very, very large, and so is mu r value, which is varying too much. And in the absence of magnetic field also they are exhibiting, and that is called as spontaneous magnetism. And this is applicable only up to a certain level of temperature. If you, it isn't applicable to all levels of temperature, and that temperature limit is called as Curie temperature. Curie limits for Curie temperature. Above Curie temperature, there won't be any spontaneous magnetism. A ferromagnetism loses its property of having internal magnetic moment. Such materials, they do have iron, cobalt and nickel. They lie in this class of ferromagnetic materials. So what actually happens in this is, see, The magnetic dipoles, they will be oriented in this fashion. They will form themselves into some sort of domains. Now, on the application of your external field, now all these domains, now they will get realigned slowly, and finally what you will see a single material where all the domains are now aligned in the same fashion of your applied electric field. This is the concept of ferromagnetic moment. Domains are observed only in these materials because you do find large number of dipoles which are already oriented in some random fashion. So they will form themselves into domain, and these domains now they will slowly increase, and finally you will experience only one particular one which is in line with the applied magnetic fields. Now, hysteresis. Now let us suppose if I take a material. Now let us suppose this is my applied field and this is my developer flux density. Now slowly, if I start applying the external field, slowly the internal magnetization goes on increasing. So all the dipoles, I'll assume that they are getting magnetized, and finally I'll be getting my B is increasing. After some time, there are no magnetic dipoles left which must orient. So even though if you apply magnetic field, there won't be any additional increase in magnetic flux. So which means that you are moving into saturation mode. Now, if you want to come back again, if you are removing the magnetic field, external magnetic field, we can't say that all the dipoles which are oriented, they won't come back to their initial positions, which means that some part of it they stay in the same fashion. This is called as residual magnetism. Okay. So to overcome this one, what you should do, you should apply a magnetic field in reverse direction, which will help you to bring down the internal magnetism to zero. And if you continue in this reverse direction itself, again you will experience a reverse saturation. Again, if you reduce, you will get a reverse residual magnetism. Again, for this one you should do this. So this is a curve. Understood? So this is a positive residual magnetism, this is residual magnetism in the other direction. Okay, so this curve continues, and this energy which is being lost in this one, it is called as hysteresis loss. Okay, now you can go through this hysteresis next class. Now we will discuss the last two types of magnetization. The first one is antiferromagnetism, wherein it is observed in special materials. One is manganese oxide, in which the adjacent ions that behave as tiny magnets, they spontaneously align themselves at particularly relatively low temperatures into opposite and anti-parallel. If you carefully see, they will oppose. So this is the way. Immediately, you will see in opposite fashion orientation is there. So which means that the dipoles, they will align themselves in anti-parallel. So because of this, there is an alignment, but overall there is no alignment. Overall the net magnetic moment is zero. So like ferromagnetic materials, antiferromagnetic materials also possess dipole moment due to spin of electron. But the opposite alignment of adjacent dipoles, it is due to exchange of interaction. The susceptibility is very small, but it is positive. It is just like your paramagnetic materials. So one such material is manganese oxide. Okay. Now the other one is ferrimagnetism. In ferrimagnetism, what happens is the magnetic moments are lined upon different sublattices in opposite directions. The major difference is that the opposing moments have unequal strengths, so a net magnetism will be there. It won't be cancelling out completely, so you will be having very small magnetism which will be appearing. And in particular, in combination of iron, particularly, you know that ferrites, particularly Fe2 plus or Fe3 plus ions, we can find this ferrimagnetism. Okay, they possess magnetic dipole moment because of the spin of electrons. Okay. So in all ferrite and ferrous ferrites, we do see that their susceptibility is also large and positive. Okay. So this is ferrimagnetism. We'll discuss in detail in the class, and that's it for today. So I hope that now you are able to classify the magnetic materials based on magnetization and try to complete this problem before you come to the class. Thank you.